Great. So welcome everyone to the QSC seminar. It's a great pleasure to have Shoy Ouseph here. He graduated from Purdue and is now going to NYU, Abu Dhabi, right? And he's going to tell us about quantum ergodicity, holography, and geometry.
Hi everyone. First of all, thank you to the organizers for inviting me to give a talk as well as with the opportunity. I am happy to chat physics. I'll be around for this entire week, so just come to my office, or if you see me around, please feel free. So to start, the title of this talk, quantum ergodicity, holography, and geometry. It's more of a dream than a reality at this point. But in this talk, I'll try to show some progress that we have made over the last year in order to realize this dream. So most of the research was done when I was a PhD student with NEMA at Purdue University. So this is just a research group. Besides the last person on the right, all of us have sort of graduated or moved to another university. So to begin with, the motivation is from holographic correspondence. So a holographic quantum field theory, basically it says that the prototypical example is the ADS-CFT correspondence, where you have a quantum field theory in ADS bulk, and that is dual to a CFT on the boundary. More formally, you can say that the Euclidean partition function of quantum field theory in the ADS bulk is equal to the generating functional for correlation functions for CFT primaries on the boundary. The main relation is that the mass of the bulk scalar field is related to the scaling dimension of the CFT operator. So in holographic field theories, it's still an open question as to how you have a quantum field theory and that produces a bulk that has some semi-classical geometric description. And the way that we're trying to approach this is from a perspective of quantum information and entanglement. So the main thought process goes as follows. Consider a thought experiment. So when Armstrong proposes thought experiment back in 2010, you take two copies of CFT on a D-sphere. The Hilbert space of these two copies will be a tensor product. So you have one state of a CFT on one D-sphere times the other state on the second D-sphere. And any pure state for these two copies will be a tensor product of psi1 tensor psi2. If you say that both the CFTs are holographic CFTs, so they'll have some geometric bulk description, and the picture, the space-time picture, will be two disconnected geometries. So that's very straightforward. Now, if we consider a thermofield double state, we can do Euclidean path integral and write down a thermofield double state, considering one boundary as one of the D-sphere and the other boundary as the second D-sphere. So this psi data is a thermofield double state. It's entangled state, and this entangled state has been shown to be equivalent to an eternal black hole in the bulk. So suddenly you had two disconnected spacetimes, but now you have a black hole with a connected wormhole between. So this is the main motivation behind saying that entanglement creates geometry, which is popularly known as VR equals CPR. And we want to approach or try to formalize this notion of how you get geometry or spacetime from entanglement. And we are trying to have an operator algebraic approach. So what we usually deal with are called von Neumann algebras. So in the operator algebraic approach, any quantum system is a von Neumann algebra with a state. Von Neumann algebras can be classified into three types. So the first type, the main type, is type 1. So type 1D and type 1 infinity are two subtypes. So type 1D is B cross B matrix algebra. It corresponds to QRIT, which is a very simple quantum system. Type 1 infinity is the harmonic oscillator. It has infinite energy levels. And so that's the type 1 infinity there. So type 1D and type 1 infinity are well understood. You can deal with them using matrix algebras. The second type main type is type 2 von Neumann algebras. So just to give a motivation, so type 1 matrix algebras. You have in a matrix algebra, you have a pure state So you have this minimum projection. You have the matrix trace. It gives you a tracial state for the system. So in type 1 mononomial algebra, you have these two. When you go to type 2, you lose minimal projection. There is no longer a minimum.
Tracial state the same as project, same as sorry, what does tracial state mean? It's an operator.
Tracial state means let's call it TR. TR is takes you from the operator to complex number, so it's a linear functional.
So it means trace.
There's matrix trace if you're using matrix algebras. It does mean trace. So the main property is the following.
Why do you say tracial state? What is the state of this tracial state?
So suppose I have a state omega. Omega of dt, if it is equal to omega of dA, this is the definition of a tracial state. If I choose my omega as matrix space, then this is satisfied. So trace of T will be the trace of T. So I can call my matrix trace as a tracial state.
A state on which a trace can be. States on which a trace can be defined.
States on which, states which have this property which you usually associate to a trace, a matrix trace.
But in finite dimensional setting, there's the identity basically up to constant multiplication is the only substate.
Yes.
So in the finite dimensional setting, tracial state just means trace. It's up to like
Yes,
constant
absolutely.
overall
Yes. In the finite dimensional setting, tracial state just means.
But you're saying that in the type, let's say other types. there
Yeah,
are
so when you
examples.
when you leave type 1, so in type 3 you don't have a tracial state. Type 2 you still have a tracial state.
But unique. When you have it, is it unique?
Up to a scaling.
Okay. So fine.
So then I guess it's an appropriate notion of trace.
Yeah. So in type 2, what you lose is the minimal projection. The minimal projection is a notion of pure state. Which means in type 2 algebras, you have no. You will have it.
Minimal projection means projection onto a one-dimensional Hilbert space.
Minimal projection means, so the dimension, it's a tricky way of saying what the dimension is of a projector, right? So you can associate the dimension of the projector by taking the face of the projector, right? So projector satisfies E square equal to P. If suppose I'm in the computational basis, and this is my P. This satisfies P. I want to know the dimension of this projection. I can take place of 0, which will give me 1. And in the matrix case, each of these have dimensions 1. Right? I could have, if I have a larger representation, this part, there is also projection to a slightly larger subspace, but it will have dimension larger than. But the lowest dimension you can have in the matrix case is 1. And in the case of type 2, there are always smaller and smaller projections. So you don't have a a minimal projection.
But all of these are projections onto an infinite dimensional subspace?
Correct.
Okay.
Yeah.
And trace is always in this type 2, trace will always give you, for projectors will always give you an integer or not?
No, not in type 2, which is why I mentioned the scaling. So type 2, 1 means it will give you a number. You can scale it down to a number between 0. Type 2 infinity means it's just infinite. Just like harmonic oscillators. Harmonic oscillators, if you try to take the trace of the maximally mixed state, it's infinity. So type 2 infinity is equivalent of that. So type 2 is mathematically well studied. Mathematicians love, yes.
Not having the minimal projections isn't the same as saying that the action of the algebra is not reducible.
Could you say
Is
that again?
reducible. Action of the algebra is reducible.
Can you say it again?
Not having a what?
Not having a minimal projection.
Not having a minimal projection. Yes.
Is it the same as saying that the action of the algebra is reducible?
The algebra is reducible.
Algebra is all operators, huh?
Reducible in what sense?
And then you can always find a smaller subspace where if you hit it with the operator, it takes you to the same.
Rather than the algebra, we are talking about the dimensional Hilbert space. So you're going into smaller and smaller subspaces of the Hilbert space. You can always find something smaller.
Such that such that the algebra takes you to itself, right?
Such that the algebra takes you to.
You can always go to smaller subspaces so that
You have the whole Hilbert space. The quantum system is described by
yes.
the Hilbert space.
But what are you projecting to?
A subspace of the Hilbert space, a subspace of the states that it can take.
Yeah, but that satisfies what property? The algebra is closed. Like the algebra is well defined.
Oh, the subspace is closed.
Under the action of the algebra.
No, I don't think so. Like a 0 would not be closed under
Exactly.
X motion. X of. It's just a subspace. The projection.
You can project down to this set, but then there is, you can, if you look at the full algebra, you have something that will take you outside of the.
Then you can say that about any infinite.
Any infinite dimensional. But in this case, yes, but we are not restricting our algebra at this point. We have the full algebra of the quantum system. We are talking about projections in that algebra.
Okay.
Can I have some example in mind for type 1?
Type 2, and that's why I left it blank. I don't need an example. So in physics, type 2 generally didn't come up until a few years. Type 2 systems have been constructed recently using cross-product instructions from type 3. Antony Speranza construction where you take a causal diamond in QFT. It has type 3 one-dimensional algebra. You cross-product it with flow of an observer. Then mathematically you get the type 2 one. And with that construction, similar construction for Trinidad wedge. If you do a cross product, you get type 2 infinity. But I don't personally understand the physical meaning yet, which is why I didn't put any examples there. Yeah.
So if I take a quantum field theory with a mass gap, I take 0, project onto the vacuum. That's a well-defined project. It projects down to a one-dimensional Hilbert space. One-dimensional subspace. You may not have a trace, but I mean, projectors exist, right? Or not down to one-dimensional subspace. Or no?
I think that would be an example of a type 1 because you're thinking of the quantum field theory on the whole sphere or something.
No, let's say our let's go to mass gap. Vacuum state is well-defined. Project onto vacuum is well-defined.
So you're talking about.
So is that not right?
That is correct. And
so even in type 3, even the worst type projectors down to one-dimensional subspaces exist.
So the confusion is because you're thinking about, so when we say quantum field theory has type 3, we are talking about local algebras. The whole algebra of any quantum field theory is type 1.
Oh.
So whole algebra is always defined as bounded operators on the entire Hilbert space, even when the Hilbert space is infinite dimensional. This is always type 1.
I see.
So yes, in that perspective, you can get, you can get the ground state. But if you look at the local region and look at just the local algebra, in type 3 there isn't even a pure state, so you can't really talk about it.
Okay, I get you. Thank you.
And this type 2, you said there are no examples, but I thought At least in Witten's lecture notes, he has these examples of an infinite chain of qubits.
Yes. So those are
Those are not
hyperfinite
Oh,
type. So I didn't put hyperfiniteness here at all. So there is something called as hyperfinite polynomial algebras. There is a construction called as a Parakiel's construction, where hyperfinite means these are polynomial algebras which can be approximated as infinite tensor products of matrix algebras, and the Parakiel's construction is basically that construction. But as an example of a quantum system where you can see it without taking the infinite tensor product, I still bring one example.
Okay, so you're saying that there's no issue with associating a simple kind of Hilbert space, matrix kind, infinite matrix kind of Hilbert space with a quantum field theory. The issue is if you want to associate a Hilbert space with a region of that.
Correct. Yes, that's exactly what it is.
What kind of polynomial algebra will be associated to quantum system which is continuum spectral, like particle free moving on x-axis? Like in these harmonic, it's bound with this discrete. In
Harmonic oscillator is discrete, yes.
And the T cross T is also discrete.
Yes.
So, but if a particle is moving on x-axis,
Harmonic oscillator wave functions are a basis for that. We're talking about the Hilbert space, we're not talking about the Hamilton. L2 shifts itself.
Okay, so type to infinity recently, there have been claims that quantum double models, especially the Tollwood, if you look at, so these are topological cases. So if you look at local algebras, they have been claimed to be type to infinity. But the paper is still unpublished, and I haven't gone through this. So type 3, again, type 3. So generally, general interacting quantum field theory, the local algebra is thought to be type 3. There are some proofs in special cases, such as a free scalar by Araki. Again, I'm lying a little bit because there's a special case where the free scalar local algebra can be type 1 infinity as well. But in general, you have type 3 for quantum field theories. Again, type 3 is divided into C0, C lambda, C1. And C1 is what quantum field theory is. I don't.
You just say once what to be subscription.
So again, these mean, so when you consider the hyperfinite case,
Okay.
right? So if you have seen it, these are tensor products of 2x2 density matrices. Generally, have lambda and then has lambda. If you put a maximally mixed state there, you will get type 2 infinity. So lambda here stands for this. This lambda in the hyperfinite construction. Yeah, so it's basically saying you don't have maximal entanglement if you were to take a bunch of qubits. This algebra, you won't have maximal entanglement. And that exactly is the reason for the lack of a tracial state. If you had half-half, it's proportional to identity, and you have a tracial state. So in type 2, you still have a tracial state. But when you get to type 3, you don't have a tracial state exactly. It's kind of non-maximum.
And whenever you're saying operators in algebra, you mean just smeared operators.
Sorry?
Smeared operators, you mean.
Smeared operators.
Not the smeared, yeah.
Rigorously, yes. Rigorously, yes. You will have to look at smeared and bounded operators. So we probably there. You look at something called as the Weil algebra. This Firetex is like your scalar field. So you're looking at bounded operators which are smooth with the Schwarz function, test function. So the test function basically localizes the operator to some algebraic region or some space-time region.
I'm really sorry to interrupt, please excuse me, but at least I can't see the board at all. So I'm just wondering, No, I won't interrupt the talk. Please excuse me. But is there some? Is it a Blackboard talk, Ouseph, or is it a slide talk? I mean, of course, you shouldn't interrupt what you're doing. But okay, does anyone know how to? Okay, never mind. Just go on. Just go on. Yeah, somehow the board isn't visible in the way the Zoom is functioning. Okay, go ahead. Go ahead. Sorry.
Can you see the slides?
I can see the slides perfectly.
Okay.
This means like
What did he say?
बोर्ड पर कवर केलाय सर मी
yeah, he has to speak somewhere else.
No, don't interrupt the talk. Don't interrupt the talk. Just in case it's 2 minutes, 1 minute interruption.
Click on the speaker, Sandeep, is the advice we're getting.
So sorry, come in person. Sorry.
No. No, that too, but with it was click on the speaker. Where you see the speaker, click on it. That was
Yeah. I tried to do that on the face. Okay. ठीक है. Go ahead, yaar. Go ahead. ठीक है. Sorry, yaar.
Is it working or no?
No, but doesn't matter. Don't worry.
So pin that window.
Yeah.
Pin the speaker window.
I pinned it. Okay. Anyway, it doesn't matter. Okay, ठीक है. Thank you. Sorry.
Speaker, you won't see the slides.
Yeah.
I pinned it. ठीक है. Okay, go ahead, please.
So I think Sandeep, you have to go back and forth between, like, you first pin whenever Shoy is using the blackboard, you pin to the blackboard, and he's using slides, you have to pin to the slides. If you can do that, you'll be able to see both.
Okay. All right. Go ahead, guys.
Yeah. So again, to back up a little bit, we were trying to figure out how geometry comes from entanglement, and we want to look at the entanglement structure.
While that's going on, right? So so this stuff is going to give us some way of defining. Suppose I just put everything on a lattice, and then I took a lattice coupling to 0. Then everything is type whatever 1. So everything is nice, and then I can take a limit. Is there something wrong with doing that, or something inconvenient about it?
There are definitely things you can do like that. So even when we deal with modular theory,
Are you able to see the board, sir, now?
Yeah, now it's perfect, and I really apologize to you all. Kapilji, let the talk go on. I'll talk to you later how to do this. Okay, now the board is perfect. Thank you. Sorry. Just let the talk go on. Sorry. I apologize to everyone. Perfect. Just go on. Sorry, I raised this issue. Thank you.
we were trying to figure out how geometry arises from entanglement. And one-norm algebras are classified based on the amount of entanglement they have. For example, we looked at why the type 3 ones can be written as the tensor product of non-maximally entangled qubits. Now, we want to approach this using one more thing, which is Tomita-Takesaki modular theory. And one-norm algebras are perfect setting for modular theory. Just from the way it's constructed, one-norm algebras have a naturally defined automorphism, which is the modular automorphism, based on which it is a quantum dynamical system. So to get to that point, we are going to work our way through classical dynamical systems and classical ergodic hierarchy, so that we can generalize it to quantum dynamical systems and talk about quantum ergodic hierarchy, and then finally get to how one-norm algebras are quantum dynamical systems. Just to as a preview, the way that this classification even came about is using modular theory and looking at the modular flow of one-norm algebras. So that is how it was classified in the beginning.
Sorry, just one second. This local algebra, local means what? There's a sense of space, real space.
Yes, there's a sense of real space time.
In principle, I could talk about phase space operators also. Like, so locally momentum space, that also has a meaning or not? Do I need to necessarily talk about some polarization of the phase space? What's local?
So from the algebraic perspective, local would be whether your algebra is commuting with the other subalgebra that you're considering, whether it's an vector space or real space. But finally, I've only thought about real space because that is when we say things don't interfere with each other and they commute. The algebras commute, so that you have a possible.
So what's the mathematical notion? It has to commute. It's a complete set of commuting.
So commutator. So if you have an operator A in algebra A and so A is an A, B is an A commutant. So this is the notion of locality that we are using. So if you have a space temperature, A and everything else is A commutant. Yeah, but it's a good question. I haven't thought about the full phase space. So the classical dynamical system is a triple. It consists of X, the measure space, on which you have the measure mu, and you have a dynamical flow denoted by T sub T. And the little t that parameterizes it can be a discrete or a continuous variable. What I mean by dynamical flow is at least a monoid. So you have group structure, but not invertibility. So if you have
but if you don't mind, if you could write a little bit bigger, I think it would be helpful for this one. But I mean, going forward. Yeah.
So we will focus only on invertible dynamical flows. So you just need to keep in mind that in general, it's usually mostly it will be okay. And for later purpose, we're going to define the sigma algebra of the measure space. So it's a subset, it's a closed subset containing space and the empty set. I'll denote it by sigma, capital sigma. The best example for a classical dynamical system is the classical phase space. Classical phase space is you have a classical system, you have the generalized coordinate Pi and the generalized moment of Pi. Classical phase space is spanned by the generalized coordinates and the generalized momentum. It's a two-dimensional symplectic manifold, which means it is equipped with a symplectic bilinear denoted by omega. And so omega is a closed form, so d omega is 0, which means the canonical volume form omega n is invariant under this flow. So the flow that we are going to consider is Hamiltonian flow. So you have a Hamiltonian function for the classical dynamical system, and you can define a vector field using the canonical symplectic 2 form. So that's given by the exterior derivative of the Hamiltonian. It should satisfy this equation with the symplectic 2 form. So that will define you uniquely this vector field because your canonical symplectic form is not degenerate. Okay. So this, along with Hamilton's equations, basically tells you that the Hamiltonian flow is time evolution. And this is the whole classical phase space of the classical dynamical system. And motivated from here, we are going to consider measure preserving flows because the canonical volume form is the notion of measure in the classical phase space, and it's preserved under the Hamiltonian flow. And we'll also consider invertible flows, which means T belongs to a group. Okay, so that was a classical dynamical system. Now to the ergodic hierarchy part. So if you have a dynamical system.
So measure preserving, I should think of as non-dissipative.
Yes.
You don't shrink down.
Correct. Yeah, the flows don't shrink. Classical ergodic hierarchy, so it classifies different types of flows based on how much of the space is covered while you're flowing with T sub T. To keep track of the ergodic nature of the flow, we define something called as a connected correlation function in terms of the measure. It is a notion of how evenly it is spread. If you take A and B, and if you flow B just for time T, let me draw some pictures. So if you have a measure space, if this is your measure space, and you're marking A and the subregion B, and you have some flow in the state case. This measures how much after some time T, how much overlap A and B have. If the overlap is proportional to how much the initial size of the objects are, then you say that you have an ergodic flow. So a dynamical flow is called ergodic if there is no subregion left invaded by the flow. That is the same, that is equivalent to, we can show that it's equivalent to saying that the long time average of an observable is equal to its measured space average, which means basically that the average probability that A and B after some time T they overlap is simply proportional to how big they were initially. It does not mean that they're not overlapping. They are going to have some overlap, but it just means that they're overlapping proportional to the volume. So that's a notion of an ergodic flow. Everything below it is also ergodic, but you have extra conditions now. You have something called as a weak mixing flow. Weak mixing flow means if the average of the absolute values decay to zero. Just from a spectral theory perspective, you can look at these flows. You can look at this dynamical flow from a spectral theory perspective. Going from ergodic to weak mixing itself tells you that you need continuous spectra for these operators. There's something called as a Koopman formalism, in which you can look at these as operators on some L2 space. If you look at the spectrum, it will immediately tell you you have stronger conditions on the spectrum of T. But we are not going to discuss that. Strong mixing is what usually you see in gravitational systems. If you take the correlation function of 2 points and you are time evolving it, or you are stretching it very far apart, you will see that the correlation function is decayed. So that is called a strong mixing. If the correlation function decays to zero in the far future, without taking any average, we call it as a strong mixing.
Okay, the correlation function means what? Yes.
Correlation function is defined as mu of A intersection BT minus the product of it. So what is the suppose it's zero, it means that A overlaps BT. The probability that it overlaps is simply proportional to how big A was in the beginning and how big B was in the beginning.
Okay.
It's called stochastic independence, stochastic independence.
So you are measuring the overlap in the phase space in case of gravity. Where are you measuring in the case of gravity?
In the case of gravity, that was more of an analogy. If you look at 2-point functions and say evolution thing, you will have your correlation function decay if you separate them. So that was an analogy.
Sorry, you mean the background gravity? There's a field on it.
Yes, semi-classical, yes.
Let also see what we see. So if I think A and B as a collection of phase space points, then the phase space points in A and the phase space points in B would sort of evolve independently, and they should not intersect.
They might intersect.
They
can intersect. The probability that they intersect should just be proportional to how big A and B were in the beginning.
I mean, in general, A and B won't intersect, but the reason they intersect is that it's the measure of A intersection T. You can keep A at fixed when you evolve, and then they can intersect.
I see. Okay, thanks.
You can take one of them to be the entire. we can take one of them to be just x. X intersection dt is already, and mu of x is 1, so it will be just 0, which means b is x just proportional to its volume.
And mu is normalized so that mu of the whole space is 1.
Yes.
So Ouseph, can I ask a simple question, if you don't mind?
Yes.
So just to make sure, long time average of an observable, I understand, and it being equal to the measure space average in your second point simply means you take that observable, say A, and average it over the entire space with the measure. Okay, so if that's equal to the long time average in a specific state you start with, and no matter what that state be, presumably, then you would call it an ergodic system or a ergodic state or something. I mean, could this be properties of states? Does it have to be true for every state? When do you call something ergodic?
So we are talking about phase space flows, right?
Yes.
So
Yes.
state space would be a point. So we are sort of looking at collections of states as well as the generalized coordinates.
Yeah, that's true. But you know what I meant was you could have some states which mix efficiently with all the others which don't do that in a general dynamical system, or no. I'm just asking, could it be some states are such that their long time average is well given by an average over all states? In other cases, no, that need not happen. Or is it just true if it happens for any one state, it happens for all? In general, in a dynamical system, what is the status?
In the classical case, if we are flowing, we are changing states. So what you're saying is, for example, if you have a submanifold in the phase space, which is determined by an energy conservation, right? Then your flow is ergodic if given enough time, the system goes through all the possible states that have that particular energy.
Okay. And then it's true for any state, because it could just be the same state started at a later time.
Yes.
Okay. Correct. Sorry. Thank you.
But just to go on with Sandeep's question, there's this KM theorem, right, which says that, if I remember right, that in the neighborhood of Gautam will know this better. In the neighborhood of harmonic points, there's this there's this neighborhood that's never chaotic. They're always
You will have periodic orbits around it.
And then you go far enough away, it can start.
Yeah.
I suppose this is the energy budget.
Yeah, this is exactly what I had in mind, Shiraz, that, you could have nice orbits and all in some vicinity, but then not other places and all, right? I mean, there can be a lot of structure, right, in phase space. Isn't that true? Sorry.
I think it's true, and maybe he's going to be labeling his orbits by, let's say, an energy or something like that, and then as a function of energy.
Yeah, I'm not going into periodic orbit theory or KM theory.
Okay.
For our case, this level is sufficient.
Okay. Thank you, Shiraz.
But typically in a dynamical system, you do have, like solar system, you do have regions where you have periodic orbits and you have regions where you have chaos. So that's the issue. Whether you choose this and A and B, these guys, to be in the chaotic subregion of the phase space or in the integrable subregion of the phase space. So
that's very correct. The thing is, we are sort of avoid that issue by looking at measure spaces, right? So these points that you're saying could be measure zero.
Not quite. That's what the game theorem comes. There's an open set around the integrable tori, which
there's an open set.
Yes, there's an open set.
I think he's just excluding all of those dynamics. He's saying there's a
But
sliver.
the measure argument will not include them because there's an open set. It's not a set of measures, if I remember that.
I at this point I don't have anything to say about that.
So if you have a time dependent Hamiltonian, is that also part of this?
the flow itself is changing. I don't think we have thought about that.
Because that could potentially provide.
I see. Would it still be an invertible flow if you have a time-dependent motor?
Sure, right? You have unitary evolution with time delay.
I was just wondering if you can avoid all these questions of K and so on.
Yeah, I don't have something to say. So the hierarchy was strong mixing is inside weak mixing, which is inside ergodic systems. So beyond strong mixing, yes.
Sorry, so if you have strong mixing, how do you avoid the myopia term when you're missing something like this?
How do you avoid?
So I thought the intuition was that A and B become completely separate when T goes to infinity.
No. They mix, but they mix in stochastically independent. They mix just based on how big they were. Yeah, this is a misconception. So this what is going to 0 is this minor. So
P of A and B is P of A times P.
Yeah. So if you think of the measure as probability, P of A intersection dt is equal to P of A times P of B.
So that's okay.
Right, which means they will mix. One intuitive example is dropping an ink droplet in a glass of water. If you wait enough time, the ink drop will just mix all over. So that's an ergodic process. Okay, so what we are really interested in, even while generalizing to quantum systems, will be Kolmogorov systems and Anosov systems. Mathematical definition for a Kolmogorov mixing system is slightly vague. So I'm going to talk about what a Kolmogorov system is. Kolmogorov mixing and Kolmogorov system, they are both equivalent to each other in the classical case. So it's more intuitive to talk about what a Kolmogorov system is. The classical dynamical system with measure preserving flow is a classical Kolmogorov system. If you have a sigma algebra of measurable sets such that you're evolving sigma naught in both the future and past, then you get sigma back. If you take the algebraic union of that, you get sigma back. If you take the algebraic intersection of that, you only have either the empty set or the entire measure space. And the most important property is something, the third one, which we'll later call as half-sided translations, which is when you're forward evolving, you're always getting something smaller.
I'm not understanding anything. What is for all A tilde belongs to sigma? What is sigma?
Oh, okay. So I'm talking about this at this point.
Okay.
We can talk about that. A and A tilde are elements of the sigma algebra.
What is a sigma algebra?
Sigma algebra is like the power set for a measure space.
For
a measure space, it's like the power set. It has all measurable subsets.
All sets that have a definite measure.
Correct.
Okay. Yeah.
All subsets that have a definite measure.
Okay, so it's some region. So A is some region.
A you can think of as some region. A tilde also is some region. Now what you do is you construct B of T, which is the sigma algebra generated by the set A tilde of T prime for all T prime less than T.
A tilde of T prime. You back evolve in T.
Correct.
And you see where A was, or everything that's now in A, where it was for all earlier times.
A tilde, yeah. You can look at that for A tilde. And now you choose B of T from the set, and you look at the supremum of the intersection. And that supremum should go to 0.
The supremum of the intersection of A and
BT, where BT is like any choice from the sigma algebra generated by back evolving A tilde.
So you're saying A primes are all algebra generated in some region of space, right? Where A and you evolve for some region of space. And now you're taking correlators between that algebra and your A.
And your A.
And your A for all choices. We see all of those correlated value. No.
In the past, yes.
Yeah, all of
So the
these.
supreme should lie, which means all of it. Right. It's an absolute value. Yeah, so the words you usually say are that if the correlations with the entire past decays to the strong mixing, you always say if the correlations decays to zero either in the far future or in the far past. So yeah, that you're right. So it means you're forgetting everything that happened in your past. So this definition is not very intuitive. So probably intuitive is the definition for modular system, where you have this property that if you consider sigma naught and you evolve it, then you get something strictly smaller at all times. The evolution is forward evolution. For modular systems, even though the definition is slightly difficult, they give rise to things that be like the entropy law or the second law of entropy and so on. So it's worthwhile to go.
What is the point number 2?
So you take the algebraic intersection of all evolutions of sigma naught.
What's the intersection?
Yes, and this is the best thing, the algebraic intersection. The algebraic. So in cases
So
of
this is the dissipative system. Is that so? Yeah, explain the third condition again.
So these arise when you have infinite dimensional systems, not compact measure spaces. When you have non-compact measure spaces, this is that is when you actually see these things. So the typical example is like you take real line and you take, for example, let's say, but then you stop at say, this was your sigma naught, and then you're evolving, so you get small. Yeah, I don't know if it's exactly the stated system. I don't have an example in mind. That's why I'm not able to say it's specific system.
So in the third step, dt, I think sigma naught is strictly smaller, or it can be equal also.
Strictly smaller. It cannot be. Yeah.
Sorry, I'm so sorry, but I maybe should have gone. But there exists a sigma algebra of measurable sets. What is a sigma algebra?
So sigma algebra is so it's like the power set.
Power set of that determined by the measure.
Yeah, it's like all measurable subsets, such that you have the empty set, you have the measure space in it, and then it's closed under finite intersection and like finite units.
Okay, so it's determined by what the measure. So given the measure, the sigma algebra is determined.
Yes.
The set of all measurable sets.
Correct.
Okay. So for all measurable sets, the first point is that you evolve sigma not in time and you get sigma. Now what is?
I think that's probably the definition of capital sigma. Is that right? One.
No, capital sigma is the sigma algebra of the entire measure space. So you have measure space X.
Yeah.
And you have the sigma algebra of that, which is capital sigma.
Actually, so in your example, if you're back evolving, then you are spanning the entire line.
Correct. And here I'm taking the union, right?
Yeah.
If I evolve and I keep taking unions, at some point
That's
I'll
the
have
whole real
entire thing. Yeah. And if I keep taking intersections, I'll have a union set.
So sigma naught is any subspace of sigma.
Sigma naught is any sub sigma algebra of sigma.
Sub-sigma.
Yeah.
One of them is also.
Yeah.
Just one.
This one.
Region.
Takes one space.
One of those.
One region and all its subsets.
I see. One region and all of its subsets. Then you take a smaller region and you evolve in time and you get the whole space. That's what the first thing is saying.
Yeah.
The second thing is somebody you guys have all understood it. Then you evolve in time and the intersection of all the spaces you get is 0.
You either get the empty set or you get the full thing.
It's translation example. So you take some box, some finite region, and then you have the translation map, and then everything is translated out.
Yeah. You get the empty set in this, we take the intercept. It should be
Yes,
more.
I mean, it's still second point. So if you start with some interval, and let's say you get a full line, right? So that's the first statement. But if I do this evolution for different amounts of time interval, why don't I get some intersection? Some subset of the full line. Because I take this and I evolve it for some t and I evolve it for some 2t, right? It would seem like whatever I evolved it in the first t would be the intersection, right?
Yeah.
Okay, whether I evolved it to t or 2t. And why would that be like null or
So it's like, so let's say you are evolving over evolution, right? You have this, next have this, and so on. So if I take the full intersection, what you have is the empty set.
How will you ever get the full thing unless sigma naught was also somehow?
Full thing is by default. It has to be a
Sigma naught has the full thing.
Sigma naught has the
Sigma
yeah.
I thought I was thinking of some smaller part.
It's a small region, all of its subsets plus the full set. Like full set comes in by default.
Yeah, I think so.
Yes, the full set.
I think the second line is not either empty set or the full set. It's just the set which contains the empty set and the full set. That's the sigma algebra. Yes.
I think it's
Yeah, sigma algebra is the subregion plus all of its subsets, like the set of sets.
Yeah, it's the set of sets.
So reminding me why I studied physics.
So, Anderson systems are basically, you can think of them as Kolmogorov systems, but in addition to Kolmogorov mixing dynamical flow, they also have exponentially decaying correlators. So they have exponentially decaying modes, which come in addition. Those are called as Anderson systems. I will give an example.
This K system are different from the system from previous slides. They both are decaying, correlators are decaying slowly.
Yeah, so in K systems, the correlators can decay, but not necessarily exponentially. In Anderson systems, you want them to
No, I'm
decay
still about in
exponentially.
previous slide, mixing of stocks.
Yes,
Here also it was decaying.
it's a different correlator that's decaying. So Kolmogorov systems are strong mixing as well.
Yeah.
So in Kolmogorov systems, you always have it always forgets about the far future or the far past. But strong mixing systems are not Kolmogorov. Strong mixing systems do not forget about the entire past. So yeah, it's a hierarchy. So all Kolmogorov systems are strong mixing. So all Anderson systems are Kolmogorov mixing. At least in this definition. Anderson system definitions slightly vary depending on where you be. So simple examples of classical ergodic systems. Rotation on a circle by a rational angle. It will take you arbitrarily close to any point on the circle. Translations on the tutorial, which is a copy of this, as long as the slope is irrational, it's the same thing. Arnold's scat map is a classical Anderson system. The dynamical flow is given by this map. And you can, so this, in addition, it has two decaying modes, an exponentially growing mode and an exponentially decaying mode. You can look at the eigenvectors for this matrix, and one of them will be an exponentially growing mode, and the other will be an exponentially decaying mode. I haven't explicitly put the calculations here. But it's an example of a classical Anderson system. So it's also Kolmogorov. So the example that we are concerned with is the Rinder wedge as a classical Anderson system.
Sorry, and that matrix had determinant 1, and that's why it was volume preserved. Is this right?
Yeah. Okay. So in fact, any such matrix with trace greater than 2, it's called a hyperbolic system. They are all Anderson systems. So consider the metric for 1 plus 1 Minkowski spacetime. So this is in the null coordinates, plus and x minus. The generators for the null translations are just the del plus and del minus. Consider a particle that is moving in a trajectory of constant acceleration. So it will follow this trajectory. X naught depends on the acceleration and e power plus minus c. The dynamics, so the dynamics we are concerned with is the dynamics that will move this particle in a trajectory of constant acceleration. It's given by the boost transformation. The boost satisfies this algebra with the null translations, G plus and G minus. So we have that the boost on a Renner wedge is a modular system along with exponentially growing and decaying modes from null translations. So this shows that it's an Ouseph system. I haven't explicitly shown how it's a modular system, but you can think of the following to see that.
Ouseph meant volume preserving?
Ouseph means exponential decay.
Decay.
Yeah, so you have extra modes, basically the ones given by G plus and G minus, which either exponentially grow or exponentially decay with respect to your dynamical flow. So here the dynamical flow is the boost.
Okay.
And if you keep applying boost because of this commutator, one is a plus and the other is a minus, so one of them will decay, the other will grow.
Either G plus or G minus. G plus grows, G minus.
Yeah.
And your full algebra is made up of only these three elements. Sorry, what does Ouseph mean? That there exists something that decays?
There exists modes that are exponentially growing or exponentially decaying apart from the dynamical flow.
Okay.
Another example is the hyperbolic upper half plane. If you look at geodesic flows, you also have something called as photocyclic flows. And those flows actually have decaying and exponentially growing with respect to geodesic flows. So those are also examples of Ouseph systems.
So if you think of these moves as leaving out the Rindler horizon, I mean, because you're only looking at the Rindler wedge.
They're not leaving the Rindler wedge. So G plus is growing exponentially, and G minus is shrinking exponentially, sort of here to there, sort of shrinking. So they're not leaving. Yeah, so to see that this is a holographic system, you can think of the following. If you take a subsim algebra and you push, this part is being pushed all the way in. So it's always strictly a subset. So if this sigma naught, when you do a boost flow, you always get something that is smaller. So that's not a proof, but it's
so simply say that again if you don't mind.
So suppose you have sigma, and if you take the sigma algebra of the Renner wedge, if I do boost, I'm always pushing it in half-sided flow. So this is called as half-sided translation, and it's strictly smaller. So this falls under the definition of a Kolmogorov system. And in addition to that, we have these P plus and P minus modes, which are exponentially growing, exponentially decaying. So it forms an Ouseph system. So now we are ready to generalize everything to quantum systems. The generalization for a measure space is called Neumann algebra. And instead of a measure, you have a faithful normal state on the one Neumann algebra. Normal is a weak continuity. You don't have to worry about it. Faithful means if an operator has zero expectation value, then the operator is zero. So one Neumann algebras along with the faithful normal state offer a very straightforward generalization for everything that we looked at to the quantum case.
So, sorry, what's the analog for the measure? Is the trace state?
A state, not necessarily the case. In general, we can define a state. A state on a von Neumann algebra is just a linear functional that maps from the algebra to complex numbers. Yeah, so it doesn't have to be fixed. And in particular relating to modular flow, if the state omega satisfies what we call as the KMS condition, then your modular flow, then the dynamical flow is the modular flow. This is a theorem from one algebra operator algebra theory saying that the only flow that satisfies the KMS condition is the modular flow given a state. In the case of finite dimensional hypersphere, is an example of such a state, that's the thermal state, and the modular flow that satisfies the KMS condition is just Hamiltonian time evolution. So let's generalize all of classical algorithmic theory to the quantum case. In the quantum version, instead of the connected correlation term, instead of the C of A, B, G, we are going to look at expectation values. Omega of A, tau T of B minus omega of A times omega of B. Here again, the flow that we are considering is a state preserving flow instead of a measure preserving flow. We say that the flow is quantum algorithmic if for all operators A and B in the one-dimensional algebra, you have the average of the connected correlation vanishing. It is quantum weak mixing if the absolute value of the connected correlation function averages to zero. And it is quantum strong mixing if for large time the connected correlation decays to zero. And this decay doesn't have to be exponential. Okay, so there's something that we can already say from this. Suppose you have, since in the thermal state, the Hamiltonian evolution is a modular flow. If you have a Hamiltonian that has eigenstates, it has point spectrum, and the corresponding eigenvalues are given the EM, you can write down the thermophile double state for which it is the modular flow as such. And if you try to connect the correlation function, you'll get this particular expression. And you can see that because you have point spectrum, you get this oscillating factor, e power I EM minus ENT. And this is in general an almost periodic function with this structure. So if you have discrete spectrum in your Hamiltonian or in the modular operator, which is the modular flow, then you can never get strong mixing. You can never get strong mixing on decay or correlation. So that's something you can already say from here. And in fact, in one of the earlier papers, we showed that if you are in a KMS state, the algebra has to be type 3-1 in order for you to have strong mixing. So quantum Kolmogorov system, what we're going to generalize is not the definition of quantum K-mixing, but the definition of quantum Kolmogorov system. So you consider one of an algebra R. R is notation for the right one-normal algebra, represented in a Hilbert space in the standard representation. And you consider a strongly continuous unitary flow so that you can write it as e power IST, and that leaves the state invariant, so you have a state preserving flow. We say that this quantum dynamical system is a quantum K system if it satisfies the analogous properties of everything that we saw earlier. Most important is the Hofstadter translation property, so that if I'm evolving a one-normal algebra, I'm always getting a proper subalgebra. And in the quantum case, quantum K mixing is not equivalent to quantum K systems. There is a separate definition of quantum Kolmogorov mixing using partitions and chaos entropy. That is not equal to the quantum Kolmogorov system definition.
Since you're using half-sided translations, so usually is this only true of the regions? What if I took a different subregion shape, a different subregion of different shapes?
You can look at see.
And if it's not a problem, we can discuss the second.
I mean, you can look at a line and translation, Hofstadter translation, a line.
Yeah, there I am.
Yeah, but that is again like the yeah.
Yes. Okay, my question was, I guess you're focusing on 1 + 1 dimensions?
Right now, I'm focusing
Okay.
on 1 + 1 dimensions. And this is in our paper, we call this as future algebra. If such structure exists, we call it as future algebra. Okay, so
sorry, what was the definition of A subscript S?
So A subscript S is you're drawing the original algebra, the algebra.
With the same Hamiltonian as.
Yes, the same. Yeah. So again, we were looking at how to get geometry from holographic quantum field theories. So the situation in which we have an example is the case of n = 4 SYM, where if you take single tree operators in the entering infinity limit above the open gauge temperature, you get a generalized free field algebra, which has been shown to be type 3 quantum algebra. So to work that end, we are going to discuss generalized free fields. Generalized free fields is a generalization of scalar free fields. So it's purely determined by its 2-point function. You are always considering a Gaussian state so that all odd point functions vanish and you have 2 endpoint functions cluster. So that the only input you need is a 2-point function. So the 2-point function is determined by something called as the spectral density. So it's very close to the Fourier transform of the 2-point function. So now what I want you to think of is, think of the holographic quantum field theory on the boundary, and you have a generalized free field algebra on the boundary. So corresponding to, for example, this interval, you have a generalized free field algebra. To be more rigorous about it, it will be the Weil algebra. And corresponding to the entire interval t greater than. So greater than t, you have another generalized free field algebra. So in such systems, you can have a second law if you have a quantum Kolmogorov system. So the expectation is that a genuinely interacting quantum system thermalizes. In particular, we expect the emergence of a second law of thermodynamics that postulates the existence of a non-negative state of non-negative function of the state called entropy, and it should be monotonic. So intuitively, we can justify this emergence of second law as follows. Consider the subspace of observables that we can access from time t to infinity and denote it by ST. So that's sort of this over here. This is a future operator system. Forward time evolution is a restriction map. So if I'm just time evolving, I'm always making the system smaller and smaller. The available algebra gets smaller and smaller. So that's given by this. The state time evolution is a half-sided translation of the future operator system. If I have an information theoretic quantity that satisfies data processing inequality or monotonicity, then I can multiply any such measure by a minus sign and obtain a monotonically increasing post-grain entropy, which is what you have in the second law of thermodynamics. So more concretely, we can consider the mutual information between the future algebra of the right boundary, h of infinity, and any subalgebra of the left boundary as an entropy function. So I'm taking the mutual information between at of infinity and b. So if I'm considering this, I can look at the boundary algebra over there. So it follows that strong substitute of entanglement entropy says that S of T1 is always greater than S of T2, just by monotonicity of the mutual information. So this Kolmogorov structure gets you a second law of entropy if you have an information theoretic quantity that is monotonic.
I mean, this mutual information you only want because you want a relative.
At this point, no, we really didn't go into anything. We just wanted a quantity that shows that you can define a
any relative entropy.
Yeah,
That's
right. Yeah.
And mutual information.
usual information in one such example here. The second law here is very general. So we looked at quantum holographic systems. The example of a quantum Ouseph system is again quantum fields on the Wendell wedge. Instead of taking the measured space, you look at quantum and algebras in the Wendell wedge. So a quantum Ouseph system is defined as a quantum holographic system with expanding and contracting unitary flows, e power I g plus minus t, that preserve the state. So the diagonal exponent is lambda here for the exponential decay or the exponential growth. We consider quantum field theory in 1 plus 1 d Minkowski spacetime and look at the algebra of observables in the wedge. The boost flow is now you can convert it into part of the algebra of observables in the wedge by integrating it against the stress energy tensor on some Cauchy surface. So it is now part of the observable algebra, and the dynamics will be determined by this boost. Just like before, if you look at null translations, generators of null translations and the boost, you will have exponentially decaying and growing modes. So you get a quantum Ouseph system in this case.
This omega here is the right triangular vacuum. Is that right?
It's simple.
Sorry?
Simple one.
Is
Because
the full Minkowski thing?
full yes. So P plus and P minus and highlight it's just a translation, right? So P plus and highlight.
Oh, this T is what? This T is the real T, right? Or no?
No, T is think of T as a translation along the null direction. Sorry, sorry.
Yeah. Yeah, so G plus and G minus are stand-in for P plus and P minus. So your T is just a variable here. I could have put S instead of G and everything.
G plus and G minus are the boosts. Sorry, maybe I got it wrong.
So G plus is like a translation. Think of G plus as a translation and
So
X plus it.
Yeah.
G plus is along this direction.
Yeah.
It's for null positive null translation. G minus is along this direction. Negative X minus translation. So you can actually go out of the interval if you just evolve it back.
Oh, okay, I see. Okay, thank you.
So now we look at half-sided inclusions, half-sided translations. We look at half-sided modular inclusions. So in quantum ergodic theory, in quantum ergodic hierarchy, even though we define quantum Ouseph systems as different from quantum holographic systems, you'll actually see that they are the same thing. So this is a theorem from Borchers, theorem by Borchers. You consider a one-line algebra and a standard GNS representation. If you have, if we have an ergodic modular future subalgebra, then the positive operator.
So what is the word future subalgebra?
Yeah, so it's the half-sided translations.
Okay.
Yeah, so it's half-sided translations. We call it future algebra in our
So
paper.
if
you have a
your
form of
system has
system,
a half-sided modular
correct,
inclusion structure.
right?
Okay.
Yes. If you have a half, yeah, that's true. So if you have a case system to be. Then the posit, so now you're taking the difference between the modular operators for the right wedge and the subalgebra A. And from modular theory, this is a positive operator. It generates a stronger continuous unitary flow, so you can write it as equal to ISG, corresponding to an NSF mode with a maximal diagonal exponent, lambda equal to 2 pi. So this part that the growth, the diagonal exponent is 2 pi is the main result of the theorem. And this is from Borchers. Now I call it a maximal diagonal exponent because recently in 2020, DeBoer and Lampro derived a bound on this diagonal exponent, assuming that if you have regional deformations such as this, there will be no more than there will be the deformation will always be at most exponential. There is no double exponential. There is no double exponential change. So this is a conjecture on the diagonal exponent. So if that conjecture is true, then it says that your Lyapunov exponent is maximal in this case.
I'm sorry, I'm following very poorly.
Yeah.
But this is this Lyapunov exponent, this Lyapunov exponent for what? Separating what things?
So it's a Lyapunov exponent for the growing and decaying modes of the NSF system. Yeah, so last time I think.
So the thing that were G plus G minus.
Yes, the lambda, yeah. So for a general quantum NSF system, you can have some lambda. But this theorem says that if you're looking at one-on-one algebra that is harmonic and has this cohomology system structure, you actually just have to buy. You don't have another choice, is what they're saying. You just have to buy. So what we end up with is that if your dynamical flow is a modular flow, and if you have a modular cohomology system, then you always have a maximal Lyapunov exponent. And you have, this tells you that you always have decaying modes, which tells you that your cohomology system is also an NSF system.
And is this somehow connected to the bound on chaos so that correlation functions will grow in real time?
So this, to my knowledge, does not have anything to do with the usual notion of chaos.
It doesn't have anything to do with the Lyapunov index of exponent of stuff.
Orthodox, yeah.
But it's the same Lyapunov, right? Or not?
No, it's not.
Oh, it's not.
But the value is the same. It's 2 pi.
The value is the same.
In principle, you could you could define an orthogonal in this setting, right?
I haven't thought much about it. I also wanted to think in that direction, but I was usually discouraged. So this is a different Lyapunov exponent. It corresponds to the NSF modes that you're talking. Not the growth of the orthogonal. So this was the main result of the paper that we published last year. So again, we are talking about these one-Neumann algebras in the boundary. Consider a pair of one-Neumann subalgebras, A plus and A minus, such that A plus is a modular future subalgebra, which means under modular flow, A plus is a cohomology system, and under past modular flow, A minus is a cohomology system. That's sort of what I've written out here. And you consider A plus flowed in the opposite direction and A minus flowed in the future direction. Correspondingly, consider G plus of minus S and G minus of S. You can show that in the scaling limit, Z plus Z minus going e power minus 4 pi is much less than 1. You can show that the commutator of G plus G minus almost vanishes. So this is written in the exponential form. If you use Baker, Campbell, Vostok, you can get that the commutator of G plus and G minus vanishes. So which means you have, so Poincare algebra is Minkowski space P plus P minus commute. You have K P plus P minus that and P plus minus K. One of the plus minus K plus minus P plus. So this part was not true. If I replace P with G plus and G minus, it's not equal to 0. But what we are saying is in this limit, you are getting this arbitrarily close to 0, and you already have this. So you are getting an approximate Poincare algebra from the boundary picture. So your algebras A plus and A minus are all generalized free field algebras on the boundary.
So can you give some physical information about what this and why are you taking this A plus and going back?
Yeah, so this is fine tuning so that you get a small factor over here, so that you have G plus and G minus is almost commuting. One interpretation of that didn't put in the correct picture. If you have a spacetime with the bifurcate filling horizon, ADS black hole or something. So this is your A plus, and this is your. So I'm flowing A plus of minus S and A minus of S, which means I'm taking A plus and making it larger and larger, and then taking A minus of this and making it larger. You can sort of think of this as sort of think of this as you're looking at a point here, you're going closer and closer to the horizon, proper distance. So all the points here, which are close to zero, proper distance is being, you're probing that region is what the geometric interpretation is. So that is why we call it a bulk interpretation of the emergent Poincare algebra. So it's an analogous near horizon. It's not exact. It's not near horizon limit, but because of this picture, we are calling this limit as analogous to the near horizon limit.
And another the only assumption here is that you have this half-sided structure.
You have this half-sided enclosure structure, yes, and that structure is in the boundary. Yes. The other reason why we say that it is the Poincare algebra is near the horizon is because G plus and G minus, if you're not in Minkowski space, they're not null translations anymore everywhere. They're null translations only on the horizons. So here, suppose this is a general bifurcate, general spacetime with the bifurcating horizon. G plus and G minus are null translations only on the horizon. Away from it, you don't really know how they're acting, because G plus and G minus were defined from the difference between modular operators. So you have a geometric action only on the bifurcating. So that is also the reason why we say that this limit gives you an emergent Poincare algebra near the horizon. Yeah, so until this was like published work from my PhD. So currently what we are trying to do is go beyond Poincare algebra. So the theorems that we used, such as the modular half-sided translation theorem, the Borcher's theorem, these are all done in the 80s and 90s. So some of them were done by Weisbrock as well. So Weisbrock had another theorem which is called modular intersection theorem. In this case, you consider two one-dimensional algebras, M, and you take non-empty intersections such that they have non-empty intersection. And they have a common cyclic and separating state. If M and M intersection N is a minus half-sided translation, and N and M intersection N is a plus half-sided translation, and it satisfies this property, then you actually have not a Poincare algebra, you get PSL2R algebra. And what we are doing now is, if you look at ADS2, ADS2 Lacoste or ADS2 Rendler, there is naturally a PSL2R algebra, a PSL2R symmetry in the metric. So we are working on the details of conformal generalized free field on the boundary and explicitly showing how we get a geometric PSL2R algebra in the bulk from these modular intercepts. And that's the end of my talk.
You try? Any questions? There were lots of questions during the talk.
I have a very general question, you'll forgive me. I understood the talk so poorly. Could you, as simply as possible, say what the physical question you are trying to answer is and what the answer is?
So the physical question was the title of the talk, basically the dream that I mentioned, which is that from the boundary, how do you vigorously say that, oh, this is what leads to an emergent spacetime, a semi-classical bulk picture. Okay. So the question that we sort of answered is, we didn't get an emergent spacetime, but we got an emergent algebra, a symmetry algebra corresponding to spacetime, which is the Poincare algebra that you find in any semi-classical spacetime.
Can you tell me there what did you put in and what came out?
So the main input was identifying a Kolmogorov system on the boundary, which we call as future algebras.
So this is this Kolmogorov system was the stuff that the past, that there's more information here than here. Was that
Yes, correct, yeah. So when you're evolving, you're always losing information.
When you're evolving, you're losing information. So this would not be true in global ADS, for instance.
Globally, no, yeah.
In global ADS, because things are periodic, you're not losing information.
yeah.
Is that the point?
Correct.
Okay, so whereas here, as you
Unless
go into the future, you lose
compact
information.
difference,
So it's like this half-sided inclusion you get talking about, right? Okay, and you say now, whenever you have a half-sided inclusion, you always have a Poincare algebra. That is your claim.
Yes. You always have an emergent Poincare.
So in any large N system, you needed large N because you were doing this for generalized PP.
Correct.
So what's the theorem is that the claim is that if you have a large N system and it is sufficiently chaotic so that you're losing information as you go to the future,
yes,
then out will always come a Poincare algebra.
Yes, from the modular flows. If your state is a KMS state, and then you will have this Poincare algebra.
So I'm supposed to deduce from this that we have this Poincare algebra is what governs its approximate. I mean, it's clearly not exactly Poincare as you said.
Yes.
What is the parameter that makes it Poincare?
What is the parameter that makes it Poincare?
It's not the scaling limit.
The scaling limit. Yeah. So this quantity should go to 0 if you want Poincare algebra.
Sorry, what was that quantity? I mean, in physical terms, if you know.
So in the boundary picture, see if there is a physical picture. So in the bulk, you can, there is a way of defining Z plus and C minus such that it corresponds to coordinates over the bulk. If I have ADS, I can always shoot the null race and define a coordinate system for this.
So that defines some time in the boundary?
Yeah, it does make to some time in the boundary. And the scaling limit is sort of like you are
going to long time.
The proper distance from the horizon is very close to 0.
Okay, so long time physics in a chaotic system at large N always has a Minkowskian kind of emergent bulk. That's your claim?
The algebra, at least, yes. If you put it in spacetime with a bucket.
Okay,
then, yes.
so I should be able to do a calculation in perturbation theory in n equals 4 angles, and I should be able to get Minkowski physics out of it. Why should I expect this to be? You know, there's hardly geometry there. But you're saying it's always true in field theory under very general assumptions. Presumably, chaotic, any finite coupling, no matter how small in n equals 4 angles, all your assumptions will be true.
It's similar to that locally everything is that space, like if you get close enough, it's like bulk point similarity, I would expect. Even globally, the space is inverse, but in local pads, it's that inverse.
Yeah, but now you have to go to that local patch. Now your space is curved on some very small scale. What in this physics is taking you to that local patch? Someone going near the horizon, the bifurcate point.
Parameter S scaling, that was a scaling again.
Parameter S doesn't help me. Just tell me what.
In the scaling
You're going near the bifurcate point, and that somehow narrows you down to one point. So you're saying that because bifurcate point sounds very geometrical to me. I mean, string scale, fuzz.
So the light rays meet in some things, the scattering can.
But even light rays, light cones are different, gets fuzzed out. When one polarization has one light ray, another polarization. I mean, the whole thing's okay, but you say there's still some symmetry related. Somehow symmetry is important, right? There's a fixed point of some symmetry. That's your Bible. Is that?
It could be that you're using like maximal chaos in some way, like this. I'm not sure what the words are.
I mentioned maximal chaos, but
so on.
Yeah, so I mentioned maximal chaos just to connect with their paper, and but the 2-by factor has nothing to do with maximal chaos.
So I mean that was not like a way of saying strong coupling.
No, not to my knowledge.
Okay, so but it must be somehow what Diksha saying, right? That you are somehow focusing on some very small region of space. Is that right?
That is true. Yes, that is true. There are ways of saying how G plus G minus actually calculates the curvature.
Are you really saying that there is this region of space? Or is there some locality in the space? Or
There's locality in the boundary theory.
Okay, so you're saying that there are these operators which somehow behave like the operators in flat space, translations in flat space, but you're not guaranteeing locality. That thing somehow it feels symmetry related. What is the symmetry? Is that right? Is that right?
No, I agree, but yeah.
What is this? So it's like an emergence of a symmetry at low energies. Is this right? Because you're going very near the horizon at the bifurcate point and you're seeing this SL2R.
By low energy?
Low energy long times.
Okay.
Yeah. You're flowing to long times and you're seeing some emergence. You're arguing that there always has to be a near horizon emergence, Riddler emergence.
In such algebras, yes.
Sounds very interesting. That's true. Thank you.
What about fluctuating plane horizons? You can have black holes with fluctuating horizons.
Yeah.
This bifurcate killing horizon, which is a property of the static.
Static, yes. Yeah.
So, but you would imagine that chaos would happen even for black holes with fluctuating horizons.
Yeah, that's a good question.
Yeah, sorry, correct. If I have the cigar, Euclidean cigar, there is a certain length scale over which, below which it looks like a patch of flat space. I would have thought that if that length scale was smaller than string scale, then you can never think of it as flat space, right? The smallest distance you can measure already sees the curvature. That's not right. You're saying that's not right.
It's large and
I'm also large. But we classical string. G string is 0. But we can test some of these things, right? We've got these SL2R Wessel-Witten theories. So, I mean, many of these things you're saying, if you can make it a question that can be tested by computing correlation functions on the boundary.
Correct. Yeah.
Can be tested.
Yeah, I'd love to do calculations to test these things. We don't have a lot of explicit calculations for most of these things.
But I mean, in these stringy realizations, perhaps is it possible that these generators are nevertheless realized some stringy way?
Maybe it would be right? It would be very interesting.
Because the statement is just about this algebra.
Yeah, right. So it's not that there is actually flat space, but it's algebra. But why should it be that? Yeah, I would like to understand. That sounds interesting.
Of course, in strong coupling,
it's obvious.
Becomes like a space-time.
Yeah.
So if you take large S, you're getting this quantifier zero in largest limit, right? If you take largest corrections, are you getting something very close to, let's say, something very similar to we get DMS or something? And then
what is the largest limit?
You are taking the largest limit, right?
Yes.
S was the parameter, right?
Yes.
And then you're getting this quantifier as a take corrections to largest limit, right? But unless corrections. I was just asking how robust is this Poincare algebra is in
Something
Can I ask one last thing? You got this result, and what went into getting it? What were the assumptions? Apart from this inclusion, nothing else? You're saying, so as long as a system behaves, as far as single trace operators are concerned, behaves dissipative. As far as I can tell. As long as that happens, so hydrodynamics should give you this. Hydrodynamics should be an example of what you're saying. Dissipative system. Stress tensor would be a. Yeah, okay, fine. So you're saying that as long as it behaves dissipative, that dissipation always implies some features of a geometrical mechanism. And where did the magic come from? So there's this dissipation, and then what? Then there's some stuff about algebras, and you get such an interesting result. Where did it come from? I mean, what was the non-trivial part?
Offside modular inclusions are a very tight structure. right?
They are, yeah.
The moment you say that those words, it already tells you that there exists some algebraic structure. I mean, there's some algebra of operators. I mean, you
Yeah,
should say
no,
that
you're right. You're absolutely right. And even just strong mixing, half-sided modular, half-sided translation is Kolmogorov structure, right?
Yeah, so it's
Even strong mixing that limits you to type 3-1. Then you're going more and more constraints.
You just put in this half-sided thing, and then what was your definition of G plus and G minus in the more abstract setting?
The difference between the modular operators.
Modular operators, what are it is?
So K would be the equivalent of
What of some type.
log of density metric.
So it's very algebra, and in a sense, it's very abstract, right? From the CFT. If someone told you this, it doesn't remind you of any geometry or anything. It's just like some abstract thing. But
Okay, sounds amazing. Amazing. So you're saying this Hamel, this I see. And somehow this thing, when we take time to infinity, this something simple, this case becomes something simple. What was this large S business in this case?
I mean, if you don't take all the way to infinity, you are exactly on the horizon.
Large S means going to the future, taking an interval to the future.
Large S means you have two algebras.
One goes to the future, one goes to the past.
Correct, yeah, but large S would mean you're making both of them the same. Because I'm taking A plus of minus S and so plus S. So this was my A minus of plus S, this was my plus of. So large S means I'm almost making both of them same.
This was all true. I mean, this you said something about this being only true in chemistry. The statement was that if there is this half-sided structure or this Kolmogorov or something.
But if you have a KMS state,
Yes.
and if you have strong mixing,
Yes.
then you're one on algebra type 3.
I see, it has to be.
Yes, yeah.
And that statement is also true the other way. If you have a type 3 one,
No,
yeah,
it's
let's
not
say
true.
it may or may not be strong mix.
Yeah, it may or may not. To check the paper, I don't remember if it's in infinity.
Okay.
I think it's in one paper.
It's only one bit. The main issue is this modular 0.
The structure of the field theory with this Lyapunov defined in a different way. Are you expecting some sort of Blackwell kind of geometry, or there's no understanding of what lip interaction, are you a strong interaction or weak interaction? Meaning, are you expecting that because of the structure of the field theory, where you have this Lyapunov and all, yeah.
Okay.
Are you expecting that the bulk has to have some sort of Blackwell?
Well, at this point, the bulk has to have some sort of horizon, killing horizon. That's the point where we are able to prove this. So, it would be black.
Any further questions? Okay, if not, let's thank Shoy again.